Hello, I'm Carol Sweeney from the Department of Internal Medicine, University of Utah. This is the lecture segment about measures of disease frequency, incidence, and prevalence for the Resident Research Modules series. The objectives for this lecture segment are going to be that students will be able to distinguish between disease expressed as a risk versus a rate, and that students will consider the treatment of time in measuring disease events. So the outline is just we'll talk about incidence and prevalence and then about risks and rates. So this is a epidemiology, public health textbook definition of incidence. Incidence is a measure of the occurrence of new disease in a defined population at risk for the disease in a specified time period. And that phrase population at risk is actually quite important. There's this concept of defining your denominator, all the people who you're going to be observing, and then those events are going to occur within that population, and then you're able to keep track of all of them. So the definition of incidence that I just gave you, as I said, is from the public health world, where the interest is strongly in measuring incidence of new disease occurrence, new onset of disease. In the clinical research setting, often people are more interested in disease outcomes. Given a population of people that has a certain disease, what is the mortality, how many are cured, what is the occurrence of adverse events. But actually, it's often very useful to use the concepts and statistical tools of incidence when we're measuring all of these outcomes. So we would just redefine our population at risk as a population who has the disease or who has whatever medical characteristic you're interested in studying, and then follow them for that outcome of mortality, cure, and so on. So this is a graphic that I like to use to show the concept of incidence. So each of these people is a person in our defined population at risk. Again, for a public health study, this might be all residents of the state of Utah, and we're going to observe them and see what the incidence of new diagnosis of, say, HIV is. So that might be an incidence study in the public health setting. So in the clinical setting, this might be the defined population of people with a diagnosis of disease X, and we're going to follow them for adverse outcome Y. But either way, we actually need to know exactly who these people are so that we can correctly observe them and correctly measure incidence. So now we've got them. We've captured them in our little circle here. We've got our whole population at risk, and we're going to start observing them, and events are going to start happening. And so each of these little red circles with a slash represents a new event as we've defined it for our study. Okay, and so there we are. We had a population at risk, and now we've observed incidence. So now what are we going to do with this information? Well, another way that I like to think about this information is that we could make a little graphic like this. And no one actually does this in a study. This is just sort of a tool in our minds that we're going to think about in terms of how our population turns into data. So in this graphic, time goes across the bottom axis from 0 to whatever time t you want to define. And then each horizontal line represents one person in the population. So this first person in the population enters at time 0 or baseline, and then is followed for some unit of time, and then at the point where it shows a blue circle, that person has been, we've observed a new disease diagnosis or outcome event for that person. And so on with each of these other lines, the person is followed in the study until there is a disease event. Thinking about the people, now each of these rows down here also represents a person in the population at risk, and these people have been observed throughout the entire time period of our study, and they've reached the end of the study, time t, and they have not had a disease event. And those are also very important observations in our study. Now, the concept of prevalence is distinguished from incidence in terms of the fact that prevalence is the number of affected persons present at a specific time in a given population. And so this graphic I like in terms of illustrating that, because you can think of this sort of laboratory beaker as representing prevalence. So incidence is the people pouring in, or the marbles pouring into the beaker, and the faster you pour marbles in, that would illustrate a situation of higher incidence. But then the beaker might fill up faster in that case, but at any given time, prevalence would be simply the number of marbles in the beaker. And then out here, the other thing that affects prevalence is marbles leaving the beaker, which would be either deaths or cures from whatever that disease was. So the concept here with this illustration is that both incidence and death or cure rates are going to influence prevalence. So now we're going to move on to the concepts of risk and rate. When we measure incidence, whether of new disease or of outcomes, we can measure that using count data, and the term that I'll most frequently use for count data is a risk, or we can measure it using person time data, in which case we would describe that measure as a rate. Disease risk is a simple measure of incidence based on count data. Other terms that might be used besides risk are cumulative incidence or incidence proportion. In a fixed population monitored over a given time period, the risk or cumulative incidence is the number of incident cases divided by the number of persons at risk. So again, looking at our graphic here, the number from 0 to n is the number of persons at risk, and the number over here shown as C is the number of disease events. So another example might be 45 people attended a picnic. Within a week after the picnic, 11 of them were diagnosed with salmonella. The incidence proportion of salmonella is then 0.24, 11 divided by 45. Or 60 patients underwent surgery. 9 of the patients had complications before discharge. The risk of in-hospital complications was 0.15, 9 divided by 60. So this is so easy. This is a simple proportion. I spent years getting a PhD. It gets a lot more complicated than this, don't worry, but this first concept is dead easy. The problem being that the cumulative incidence can only be calculated from a closed population. That is to say, you must have complete follow-up on each person. But what if you have a dynamic population? Most populations are not closed, they are dynamic. So the idea being that new people could enter the population. So if we go back to our population of residents of the state of Utah, new people are moving in. In fact, they're moving in faster than people are moving out or dying. People are being born. So our population is constantly changing with people entering. And also, when you're conducting a study, new participants are enrolled in your study at different times. Think about a randomized trial. You don't just pick a day to be day 0 and you enroll all of your participants on the same day. You identify an eligible participant, you enroll them, you randomize them, and then a week or 10 days later you identify another participant, and so on and so on. So they all are going to have slightly different amounts of follow-up time. They are not going to be a closed population with all one amount of time followed. Also, people can move away, people can die from other causes, and researchers can lose contact with some people. So all those issues mean that we can't draw that simple graphic that we drew before, where everyone who does not have a disease event is followed all the way to the end of the study time. Instead, we end up with graphics like this. So the same part at the top are people who have a disease event indicated by a closed blue circle. But down here, now we've got some individuals who are followed for a certain period of time, and then their follow-up stops. So we would describe those people as censored or lost to observation. So the person I just circled is lost to observation at time 1. Here's a person who's lost to observation at time 3. And again, sometimes that's actually something went wrong. That person was lost. They didn't come back for their study follow-up visit. But other times that's simply that person was enrolled in the study only 1 month ago, and the other person was enrolled in the study only 3 months ago, and therefore we only have that much follow-up. So either way, we have to have a way to address this issue when we're measuring disease incidence in our population. So to do that, we're going to use the concept of person time. Each subject contributes person time to the denominator equal to his or her time under observation and at risk. So the incidence density, the incidence in a dynamic population, one way of describing it is an incidence density. Another way is just to call it a rate. So it's going to be the number of new cases divided by the person time at risk. So here's our graphic again. In each of these people, we are going to decide how long they've been observed. So these people have been observed for only 1 unit of time. These people have been observed for 6 units of time. This person has been observed for 3 units of time. So they each contribute that many units of time to the denominator of person time. And then we're going to calculate the incidence rate exactly from that graphic. So there were 8 incident disease events. That's our numerator. The denominator is to multiply these different units of time times the number of people who were observed for that length of time. So we get a total of 84 months. So 8 events divided by 84 months gives us 0.095 events per person month. And note that the units of incidence rate are reciprocal time. An expression of an incidence rate must include time in the denominator. So in summary, measuring incidence depends on defining the population at risk and observing outcomes in all members of the population. And that concept becomes really important when you're thinking about studies where we're trying to look at cause and effect. Whatever that outcome is, the effect, we want to make sure that we've properly followed all of our population at risk so that we're not biasing our study of those outcomes in relation to whatever the treatment or cause that you're interested in is. Measures of disease outcomes such as mortality can be based on the same concept as incidence. And the final thing to remember is that the term rate, if we're going to be really strict with our terminology, the term rate is used in the strict sense only when the denominator is time. You'll hear people say rate about a lot of other quantities, but in terms of statistics and epidemiology, a rate is a quantity with units of reciprocal time. Thanks, and there's another segment that follows this, which is about measures of disease frequency using survival.